Mars, the red planet. For centuries, it has captured the human imagination, a beacon in the night sky, a canvas for legends of alien civilizations, a mirror reflecting our hopes and fears about life beyond Earth. From the vague outlines of canals seen in the telescopes of early astronomers to the desolate and magnificent reality captured by modern robotic probes, our understanding of Mars has evolved. But a profound question always echoes: are we alone? Today's cold, dry, and radioactive Mars still hides the answer: not active life as we know it. Or maybe the echoes of life. Signs of ancient life billions of years ago, when Mars was very different from what it is today. Join us on a journey through billions of years of planetary history and decades of relentless exploration. We will pursue clues etched in rocks and comb through complex chemical data, transmitted millions of kilometers to get to the heart of the mystery. Are there secrets of ancient life buried deep in the red sand? To understand the search for ancient life, we have to go back in time. About 3.5 billion or even 4 billion years ago, Mars was not the cold desert it is today. Evidence on its surface tells of a warmer, wetter world. Orbiters, like eyes in the sky above Mars, have mapped hundreds of kilometers of dry river channels, testifying to once powerful water flows. Deltas, like the spectacular landscape in Jezero Crater, which Perseverance is exploring, record the edges of ancient lakes, where rivers slowed their flow and deposited layers of silt that accumulated over millennia. This hydrological history has been confirmed by robotic geologists on the ground, who have touched Martian rocks with their own hands. Rocks that needed water to form have been found. Sedimentary layers like those in ancient lake and river beds on Earth. Clay minerals and hydrous sulfates have been detected. Specific minerals that are the chemical fingerprints of the presence of liquid water. From a lost realm of liquids. Water, the main solvent for life. Energy perhaps from a younger sun or from underground volcanic heat. Organic matter, carbon-based molecules, the building blocks of life. Perhaps brought in by impacting asteroids and comets or formed naturally by geological processes. These are key ingredients for life. The evidence suggests that early Mars seemed to have it all. It would have been a habitable world. But this world that could have supported life didn't last. About 3.5 billion years ago, something radical changed. Mars began its slow transformation into the inhospitable planet we see today. The primary reason: the loss of a global magnetic field. Unlike Earth, where a boiling molten core generates a protective magnetic field to shield it from harmful solar radiation, Mars' internal dynamo seems to have shut down long ago. Without this invisible shield, the relentless solar wind, a constant stream of charged particles, began stripping away the Martian atmosphere, molecule by molecule, over millions of years. Atmospheric pressure plummeted, and liquid water could no longer exist on the surface, either evaporating into the thin atmosphere or freezing in the expanding polar ice caps and underground permafrost. The planet dried and froze. Crucially, the loss of a thick atmosphere meant a loss of protection from intense solar and cosmic radiation. The surface became, and remains, a raging warren of high-energy particles, a sterilized environment that is extremely hostile to complex organic molecules and known life forms. If life had arisen on early, wet Mars, could it have survived this climate change? Did it retreat to underground shelters? Or did it disappear entirely, leaving only tiny traces? Fossils or chemical fingerprints, sealed in ancient rock layers that had survived the harsh surface environment. Thus began the search for ancient signs, a beginning that has grown more determined. In the 1960s and 1970s, humans first came into close contact with Mars via NASA's Mariner probes, which revealed a cratered, moon-like world. These initial observations undermined previous imaginations of a thriving ecosystem. But the question of life still lingered. In 1976, humans landed on Mars for the first time on a dedicated life detection mission, Viking. Two eponymous landers landed hundreds of kilometers apart, carrying miniature laboratories to conduct experiments. The core goal: to collect Martian soil and directly detect current biological activity. Martian microorganisms breathing, eating, and surviving in the rust-red dust. Of the three complex biological experiments, two were negative or ambiguous, but the labeled release experiment caused heated controversy. The experiment added a nutrient solution containing radioactive carbon to the soil sample. The principle is simple. If microorganisms are present, they should metabolize nutrients and release detectable radioactive gases. As a result, the gas release continued. Further experiments showed that the reaction of the control sample that was preheated and sterilized stopped. A perfect simulation of the biological response. However, the excitement was almost immediately dampened by another key Viking instrument, the gas chromatograph mass spectrometer (CMS). This instrument is designed to detect organic molecules, carbon-based substances that form the basis of life as we know it. The GCMS analyzed the soil and found essentially nothing. The organic compounds were present in such low levels that they were initially considered potential contaminants that might have been carried over from Earth. How could biological activity exist without the organic molecules that make up life? This paradox puzzled scientists. The general scientific consensus, formed over several years of analysis, ultimately favored a non-biological explanation. Perhaps highly active chemicals in the Martian soil, such as peroxides or, as later confirmed by the Phoenix lander in 2008, colorates, mimicked the signature of life in a labeled release experiment through pure chemistry. The Viking mystery left a complicated legacy. It completed humanity's first and so far only, dedicated search for active life, and its results are still debated by some to this day. More broadly, it reveals the enormous difficulty of remotely detecting extraterrestrial life and highlights the critical need to prioritize understanding the unique geological and chemical environment of Mars. The problem has not been solved, but simply put aside, awaiting the arrival of new methods. After Viking, the focus of Mars exploration shifted. Rather than searching for life itself, a new generation of missions sought to understand the Martian environment, especially its historical connection to water. Could we find definitive evidence, not just of a fleeting flood, but of a persistent body of water that could have supported life? In 2004, a new era of surface exploration began with the arrival of twin robotic geologists, Spirit and Opportunity. Designed to last just 90 Martian days, the two rovers roamed the red planet for years, far exceeding expectations and completely overturning our understanding of Martian history. Their mission statement: follow the footprints of water. Spirit landed in Gusev Crater, a huge basin that orbital images suggest was once a lake. Although it was disappointing to see that the flat areas of the crater floor were covered by younger lava flows, Spirit eventually climbed the nearby Columbia Hills. There, it found striking evidence of past water activity, including deposits of nearly pure silica, indicative of an environment where microbes could thrive, such as ancient hot springs or volcanic steam vents, common on Earth. Opportunity landed halfway across the planet in Meridiani Planum and made an immediate scientific breakthrough. It bounced into Eagle Crater, exposing bedrock layers directly for instrument testing. Analysis of those rocks revealed chemical and mineralogical evidence, including goethite. That clearly points to an environment in which acidic, briny, standing water formed, conditions typical of such minerals on Earth. Later explorations of large craters, such as Endurance and Victoria, revealed more signs of water activity both above and below the surface. Crossing treacherous sand pits, withstanding equipment failures, enduring dust storms that sweep across the globe, and enduring the freezing cold of the Martian winter, Spirit and Opportunity have far exceeded their design lifespans. As humanity's first mobile geologists on Mars, they cut through the red dust and revealed the dynamic hydrological history hidden by the wind and sand. They confirmed the existence of habitable environments on ancient Mars and paved the way for next generation of probes, those tasked with exploring more complex clues, including the building blocks of life. Building on the groundbreaking discoveries of Spirit and Opportunity, NASA launched Curiosity, the largest and most advanced rover yet. In August 2012, it landed spectacularly in Gale Crater using an innovative sky crane maneuver. This SUV-sized mobile science laboratory is designed to assess the past and present habitability of Mars with unprecedented precision. Gale Crater was chosen because of the layered rock mountain at its center, Aeolus Mons, informally known as Mount Sharp. The mountain is like a geological history book, with layers that may record millions or even billions of years of environmental change on Mars. Curiosity's mission is to drive to the base of Mount Sharp and decipher that history layer by layer. Early in the mission, even before reaching the base of the mountain, Curiosity drilled into fine-grained sedimentary rocks at a site called Yellowknife Bay. Analysis revealed the presence of clay minerals, sulfides, and low levels of salt, strongly suggesting that an ancient freshwater lake, perhaps even potable by Earth standards, had existed there for tens of thousands or even millions of years. This is a clearly habitable environment. Crucially, Curiosity's Advanced Sample Analysis at Mars (SAMP) instrument detected preserved organic molecules in the ancient laked mudstones. These are not complex biomarkers, but simpler carbon-based molecules such as chlorobenzene. Subsequent exploration of other rock layers also found thiophene, benzene, and toluene. Finding these organic building blocks preserved for hundreds of millions of years in a confirmed habitable Environment is a milestone. It means the raw materials for life once existed, and more importantly, it proves that ancient carbon chemistry in rocks near the surface of Mars can be preserved for a long time. However, the radiation detector, RAD, carried by Curiosity continues to measure high-energy particles from space. The data show the harsh reality of the surface of Mars. The radiation intensity of galactic cosmic rays and solar particle events far exceeds that of Earth, which poses a major challenge to the long-term preservation of complex organic molecules near the surface and a huge obstacle to future manned exploration. Curiosity confirmed that Gale Crater was habitable in ancient times and found organic building blocks that have been preserved to this day. But the hard evidence of life itself is still missing. Maybe they never existed. Maybe billions of years of continuous radiation have destroyed them, or maybe they are hidden deeper beyond the reach of Curiosity. With the arrival of NASA's Perseverance rover in February 2021, the exploration has become more focused and in-depth. Its destination is Jezero Crater, a well-preserved ancient lake and river delta system. Scientists believe that this is one of the best places on Mars to look for potential signs of microbial life, or biomarkers. The so-called biomarker refers to any substance, object, or pattern that must be formed by biological action. It may be a complex organic molecule, a specific mineral combination, a microscopic physical structure unlike anything, or even a pattern left in the rock texture by a microbial community. Perseverance carries a series of instruments whose goal is not only to assess past habitability, but also to actively look for these potential evidences and accurately locate them where they were formed. The ultraviolet laser spectrometer, SURLOC, and the micro-area X-ray spectrometer, PIXL, installed on the rover's robotic arm, work together to analyze the elemental composition, mineral composition, and most importantly, anything, the distribution of organic molecules on the surface of the ground rock at a microscopic scale. They seek to capture patterns and concentrations that might suggest microbial activity, such as fossilized remains of microbial mats preserved in rock textures, or enrichments of specific organic compounds that are difficult to explain alone by geological processes. Perseverance has found rocks rich in a variety of organic molecules on Jezero, confirming that this ancient lake and delta environment has excellent preservation potential. It has studied volcanic rock layers and river sediments, outlining an increasingly complex and fascinating picture of Jezero's history. The rover even carried Ingenuity, the first helicopter to fly on another planet, to scout the terrain ahead. But Perseverance's most critical and unique mission is to serve as the first stop in the unprecedented Mars Sample Return program. It is carefully selecting locations with high scientific value drilling core samples of rocks and regolith about the size of chalk, encapsulating them in sterile sampling tubes and strategically storing them on the surface. These samples, like messages in a bottle, are waiting for future missions to collect them and eventually return them to Earth, because verifying key evidence of ancient life on Mars may require laboratory analysis capabilities far beyond the rover's payload. Although rovers like Curiosity and Perseverance can scrape the surface and drill a few centimeters deep, the harsh conditions on Mars, especially the constant bombardment of high-energy radiation, raise a key question. If ancient life existed, is the surface really the best place to look for intact remains of it? Many scientists believe the most promising exploration target is deep underground. There may be well-preserved biomarkers or even microorganisms that survive in isolated, protected micro-environments today. Just a meter or two below the dusty surface, the overlying rocks and soil significantly attenuate damaging cosmic and solar radiation. Temperatures are more stable too, avoiding the dramatic daily temperature swings that occur at the surface. What's more, it's more likely to find reserves of liquid water underground, not in pure lakes or rivers, but perhaps in the form of highly saline brines. Such liquids can remain fluid at temperatures far below the freezing point of pure water, and their heat may come from geothermal activity below or from interactions with salts in the rocks. Future missions are being designed with the potential of the subsurface in mind. The drill on board Rosalind Franklin, the European Space Agency's ExoMars rover, can drill down to 2 meters, far deeper than any previous Mars mission, specifically large of soil and rock sample, and may be less affected by the harsh conditions on the surface and be contained more intact organic matter. Meanwhile, the Mars Express Orbiter's MARSES radar, the Reconnaissance Orbiter's SARAD radar, and the Perseverance rover's REM-FAX instrument are using ground-penetrating techniques to peer beneath the surface, mapping ice and rock layers, and even detecting liquid water underground. These tools provide guidance on the best places for future drilling or exploration. Other concepts include exploring Martian caves or lava tunnels, natural tunnels formed by ancient volcanic activity that could provide vast, ready-made shelter from surface conditions. Whether it's the search for ancient life on Mars, a potential for existing life, the quest is increasingly pointing to an unknown world deep beneath the red sandstone and rock. To guide Mars exploration and understand the faint signatures of life that might appear in such an alien environment, scientists look to Earth's extreme environments. Areas that somewhat mimic Mars conditions. These places are called Mars analogs. They tell us how life adapts to seemingly impossible conditions, how it survives, and, more importantly, what traces it might leave in long-term, harsh, geological environments. In Chile's hyperarid Atacama Desert, one of the driest places on Earth, with intense ultraviolet radiation similar to that of Mars. Microbes hide inside salt crystals or deep below the surface to avoid the deadly sun. Studying these organisms provides a strategy for searching for life beneath the Martian surface and in specific mineral types. The Antarctic dry valleys are cold, dry, and windy, and were once thought to be devoid of life. But simple microbial ecosystems exist in rock pores, endoliths, or beneath ice, and their slow metabolism and survival strategies provide models for studying potential Martian life. Even deep in the Earth's crust, miles below the Earth's surface, scientists have discovered thriving ecosystems in mines and boreholes that are completely shielded from sunlight. These microbes rely on chemical energy produced by the interaction of water with rock, chemosynthesis, to survive. This provides a powerful model for potential subsurface life on Mars, which could persist in deep environments through similar water-rock reactions. From hypersaline lakes to acidic rivers, from volcanic hot springs to the frozen Arctic, life on Earth has shown amazing adaptability and continues to expand the known boundaries of life. Studying these extremophiles not only brings hope, but also improves our exploration strategy and provides key insights and search templates for identifying potential biomarkers on Mars, whether ancient or existing. While our rovers are already doing incredible science on the Martian surface, analyzing rocks and soils with onboard microlabs, the ultimate proof of ancient life, evidence that will withstand the highest level of scientific, will likely require full analytical capabilities of Earth-based laboratories. That's the core goal of the ambitious, multi-phase international effort called Mars Sample Return. The Perseverance rover is the first step in the effort, selecting the most scientifically interesting samples and sealing them securely on the surface. Subsequent plans include sending a precision lander, the Sample Recovery Lander, to the Jezero region. The lander will carry a small collector vehicle to retrieve the sample tubes left behind by Perseverance. Once collected, the precious samples will be placed in a protective capsule atop the Mars Ascent Vehicle (AV). The MAV will be launched from the Martian surface. First time humans have launched a rocket on another planet, carrying the sample containers into Martian orbit. In orbit, the Earth Return Orbiter, built by the European Space Agency, will perform a complex rendezvous mission. Autonomously capture the sample container in orbit, seal it in another layer of biocontainment, and then ignite and set off to start the long journey back to Earth. If all goes well, this capsule containing only a few hundred grams of carefully selected Martian rocks and soil will land safely on Earth at early to mid-2030s. These precious materials will be handled with extreme caution and will only be operated in highly secure deaded biocontainment facilities in the early stage, preventing the samples from being contaminated by the Earth and avoiding potential unknown Martian biological hazards. Although possibility is extremely low, threatening the Earth, the Mars Sample Return Program is one of the most challenging robotic space exploration projects ever undertaken. It is technically difficult, complex, and expensive, but the potential scientific rewards are incalculable. Bringing uncontaminated Martian samples back to Earth to study them with the most advanced instruments, equipment that cannot be sent to Mars due to its size, complexity, or energy consumption, or even technology that has not yet been invented, may be our best chance, or even our only chance to definitively answer the ultimate question of whether there is life beyond Earth. If evidence of ancient life on Mars is found in the returned samples, it will completely overturn our understanding of the universe and forever change our place in it. Despite the amazing achievements of our robotic explorers, the ancient dream of sending to Mars lingers. Despite the enormous challenges, how to protect astronauts from radiation during the long journey, and on the Martian surface, how to provide reliable life support systems, how to cope with the psychological stress of long-term isolation, and how to ensure absolute safety during the round-trip journey. Human explorers have unique advantages. Astronauts on Mars, especially those with geology and field science training, can bring human intuition, adaptability, and problem-solving skills directly to the exploration site. They may be able to identify potential geological targets more keenly than robots, operate deep drilling equipment to obtain vital underground samples, and perform complex field analysis, greatly accelerating the search for signs of ancient life buried deep in the planet. The technical, physiological, and financial barriers remain daunting, but the vision of humans stepping onto the red dunes and personally extending the boundaries of perception and exploration a powerful driving force for future space exploration. Billions of years ago, Mars was a warm, wet, vibrant world that could have bred life. Today it is a cold, dry, radiation-ridden desert. Yet tantalizing clues remain, engraved in the landforms of ancient riverbeds and deltas, sealed in the chemical structure of hydrous minerals, hidden between simple organic molecules, preserved in ancient rocks, and perhaps even buried deep in the vast, unexplored underground. Our robotic pioneers follow the water trails, analyze the chemical signatures of habitable environments, formally launch the search for biomarkers, and even begin collecting samples that will eventually be brought back to Earth to reveal the ultimate answer. The question still hangs in the thin atmosphere of Mars. Did life ever exist on Mars? If so, can its fragile traces withstand the erosion of time, atmospheric loss, and radiation bombardment, waiting for human discovery deep underground? The search continues. Every mission, every rotor rotation, every drill sample, every string of data that travels across the stars brings us one step closer to the truth. We are listening to the faint echoes of lost worlds, even whispers of an oblivion biology, buried deep beneath the red sands of Mars. Whatever the answer, it will radically reshape our understanding of the nature of life and our relationship to the universe.